Hello friends, welcome back. In this video, we will be studying about a very popular dimensionality reduction technique, which is principal component analysis. Principal component analysis. Right. So, what is this principal component analysis? Is another popular dimensionality reduction technique, which is very widely used in all data analysis and machine learning algorithms. Right. So what actually happens here is we are transforming the entire high dimensional data into a new coordinate system. Right. So the new axes which are formed will be called as principal components. Right. Say suppose I have a three-dimensional data. I am trying to convert that into a two-dimensional or in terms of PC1. PC stands for principal component 1 and principal component 2, right? Where the principal component 1 captures the maximum variance in the data, while the remaining part variance, the maximum remaining variance is which is orthogonal to the PC1 is plotted in the form of PC2, right? So we will be speaking about principal component 1 and principal component 2. Right? Principal component 1 will be indicating the capturing of maximum variance. Okay, and PC2 also captures the same thing, but the remaining variance. Okay, and remember the PC1 and PC2 are orthogonal to each other, right? So when I say anything orthogonal to each other, that means they don't influence each other. That is a meaning. Whenever I say independent of each other, that means that they are independent of each other. They are not influencing one another, right? So now, why is PCA useful? PCA is very widely used. Say, suppose I have data with 10 features. Now I want to reduce to two or three features while it's not data elimination. I'm not eliminating any of the features. If I say data elimination, that means uh, among 10 features, I find randomly or strategically, I will pull out some of the data. So that becomes a data elimination. But if you eliminate some kind of a data, what happens is, so the important information associated with that feature will also be getting lost. Hence, I don't want to go and eliminate some of the data. Instead, I want to reduce the dimension of my data. Say the 10 dimensional data, uh, 10 features ka data. So I have to reduce it to now two to three features such that the important information of the data is retained, right? And the second advantage is I may not be able to handle all higher dimensional data. So if you want to visualize some data, it's always good that you reduce it to lower dimensional data and so that um, you can easily visualize it. So, and also there are some other advantages like I will be able to reduce the noise because whatever is a small variation directions which are small uh, which are introduced due to the noise, signals can be just removed by using the dimensionality reduction techniques. Okay, so these are the advantages of why PCA work, why PCA is so useful, and the PCA steps are nothing but as we solved some numericals in the classroom also, right? So PCA, the first and foremost thing is we did find out the centroid or the mean of the given data. The second one is we were trying to compute the covariance matrix, and third, we were trying to compute the eigenvalues and eigenvectors. Then, with the help of eigenvector, so PC1 we have considered in the numerical as well, right? So why PC1? Because It is a maximum variance, the signal with a maximum variance. Then orthogonal to PC1, we have drawn the PC2. Right. So now once your PC1 and PC2 are identified, now we will be porting our data into a new coordinate system. Right. So that is how uh, we will be dealing with a high dimensional data and reducing its dimensions with the help of principal component. Right. Those principal components are nothing but so PC1 and PC2. Right. So that's about the prerequisite theory required for understanding the implementation. So we will see you again back in the implementation video. Thank you.